So this is a tool presentation paper, but I'm including quite a bit of motivation and discussion as to why we're doing this as well. A lot of the work on the VeriPB tool was done by Stephan, who is at the doctoral program, so you should certainly talk to him if you find this interesting. So what's the problem I'm trying to solve here? There are a lot of dedicated solvers for hard problems. We have the general purpose solvers, constraint programming type solvers, as well as, for example, for graph algorithms, which I work on a lot, we have dedicated solvers for clique and subgraph finding and so on. But a lot of these solvers are buggy, including solvers that are very commonly regarded as state-of-the-art. And unfortunately, to make matters worse, these buggy solvers nearly always produce the right answer, so it can be quite difficult to detect when we have a problem. And aside from being annoyed at this from a scientific perspective, there are broader consequences to these buggy solvers. We are using optimization technologies for things like kidney exchange and allocating pupils to schools. So these are potentially life or death or very high impact decisions. And in constraint programming, we're in the interesting situation that we have at least some notion of what the right answer is, unlike, for example, machine learning, where you can't really define what the problem you're trying to solve is. So really, we should be looking very hard at making sure that our solvers are actually producing the right answer, at least assuming that we've modeled the problem correctly, of course. But you don't need to trust me that these solvers are buggy. You can trust Peter Stuckey instead. Here are some slides from a talk he gave at KTH a while ago. So commercial MIP solvers are buggy. CP solvers, lots of our CP solvers are buggy. SAT solvers, slightly different situation depending upon what you're doing. So how do we solve this? Because the traditional software engineering answer is to use testing. But testing, I found, is not very good at catching non-trivial bugs. And even if you assure me, look, my solver has been very carefully tested, it's quite difficult for me to believe you at this point. I've seen so many buggy solvers that I am very skeptical of people who say we tested it. So what's about formal verification? The difficulty here is the cost. There are estimates that it takes 100 times as long to implement a formally verified algorithm compared to the algorithm itself. And the algorithm you end up is often not very performance suitable. I believe, for example, there is still not a fully verified all different propagator. So what about proof logging? The idea behind proof logging is that a solver doesn't just output a solution. When it outputs a solution, it outputs a proof that its solution is correct as well. And the key point here is it lets us trust solutions rather than solvers. So we can detect if a solver ever produces an incorrect answer, even if this was due to, for example, a hardware error. It doesn't mean the solver is correct. It means if the solver is wrong, we will definitely know about it. And proof logging is indeed fairly standard in the SAT community, at least if you're only solving basic CNF problems, and if your solver doesn't do cardinality reasoning, doesn't do Gaussian elimination, for example. The problem is, if we encode some constraints this way, we end up with an exponential blow-up, which completely kills performance. It loses all of the advantages that CP has over SAT. In fact, even small polynomial blowups are really bad in practice when we're talking about proof logging. The problem here is that the SAT proof logging technologies use a very simple proof format, which closely mimics what simple SAT solvers do, but not what constraint programming solvers or dedicated solvers for graph problems do, for example. Now, we could go with very rich proof logs, so we could put every propagator into a proof log. So you just say, hey, I called the all different constraint here. The difficulty here is that these proof logs are very difficult to verify and very difficult to trust the verifier. Propagators are where most of the bugs are in constraint programming solvers, so we really want to be careful here. We are now claiming we have the solution to this. What we want is a proof language which is very easy to verify, so it doesn't require any hard work from a proof verifier. We want something that's really easy for solver authors to work with, particularly if we're pushing to adopt proof logging as standard. We want something that can be added into existing solvers without too much work. And we need something which is powerful enough to express combinatorial arguments very compactly. If you work with, for example, resolution proofs, you have an exponential blow up on even simple things like pigeonhole arguments. So all diff is very difficult. We want a proof system which is both possible to explain this sort of thing compactly and easy for solver authors to deal with. And we believe this is what VeriPB is providing to you. So what's the process of creating a trustworthy algorithm? First thing you need to do is describe your problem. Now, we don't in general have a single standard format for describing problems. Here, we're going to use pseudo boolean models for a reason I'll discuss later. So take whatever your problem is and express it as a pseudo boolean model. Then you have to produce a proof log. So you write out a small header. Then every time you backtrack, your solver needs to output something called a reverse unit propagation statement. I'll explain this a bit more. Every time you find a solution, or if you're dealing with an optimization problem or enumeration problem, every time you find a new increment or a new solution, you output and you record it. Again, that's very simple. And if your propagators do something clever, then you need to do something to justify what they're doing. You run your solver and your solver finishes by asserting contradiction. So now we have the pseudo boolean model and we have a proof log file. We run this through a VeriPB tool, which either says, yes, that's fine, or no, that is not a valid proof for what you gave me. And proof verification, I must stress, is very simple. So no search, for example. A proof verifier is a very simple piece of code. We know that a distracted PhD student can write a proof verifier in an afternoon when they're supposed to be working on something else. So what's a pseudo boolean problem? A pseudo boolean problem is just a mixed integer program where every variable has domain 0 to 1. And just as a bit of convenience, I'm going to be calling my variables x something in this talk, and xi with a bar over it just means 1 minus xi. And because of this, CNF can be written directly in pseudo boolean forms. If I have x1 or not x2 or x3, that's the same thing as saying that x1 plus not x2 plus x3 is greater than or equal to 1. So we already know how to write CSPs in SAT form in various different ways. We can do that, but pseudo boolean makes this even simpler, and simple is important because this isn't formally verified with our tool. Just very briefly, this is roughly what an OPB file looks like. So you can read the constraints as a sum. I'll not go into the details on this. And again, very briefly, we can take constraint programming variables and we can very easily express them as an OPB file just by saying, okay, this every variable we encode using a 0-1 encoding has to take a value, at least one value and at most one value. And again, we can encode constraints. If you've ever seen encoding CP constraints to SAT, this is the same process of pseudo boolean modeling, but it's a bit simpler sometimes. I mentioned reverse unit propagation, just to give you a rough idea of what this is. Unit propagation for a pseudo boolean model is integer bounds consistency. If you're dealing with CNF clauses, then it's the same thing as unit propagation in a SAT solver, but with pseudo boolean constraints, it's a bit more general. And if I give you a constraint speculatively and say, okay, I want to assert this new constraint also holds. What we do, we take the negation of this constraint, add it to all the existing constraints we already have, and unit propagate. Now, this leads to unsatisfiability. We can obviously assert the new constraint and just add it to all the constraints we know. This is the key step behind proof logging. And in practice, what this means is that all solvers need to do to become trustworthy is whenever they backtrack, they just need to output the trail using a reverse unit propagation statement in the proof log. No need to worry about the details of exactly how that's proved. You just output a reverse unit propagation step. Very briefly, this is what a proof log looks like. The first two lines are a header. The 2 lines that start with O are objective functions. This is for an optimization problem. I'll discuss this a lot more in my talk in the main CP conference and run through this. The use statements are just asserting a trail. So the first use statement here says either x12 is false or x7 is false, and then we backtrack again and say either x12 is false, and so on. What about cutting plane steps? So we use these when reverse unit propagation is not enough. So for example, for the all different propagator, if we find a whole set, this is not something that follows by unit propagation. In the cutting planes proof system, we can add constraints together, we can multiply constraints by constant, and we can divide with rounding up. And it turns out this is sufficient to very easily express, for example, an all different failure. So if you have a rough idea of how the all different propagator works, it finds whole sets. So here we would find W, X, Y, Z as four variables. They have only 3 values between them. And a very brief sketch of what a cutting planes proof looks like. So we have constraints saying that every variable has to take at least 1 value. We have constraints saying that each of those values can be used at most once. And it turns out you just add all of the things together and the proof just works out. So you just add everything up and you end up with 0 is greater than or equal to 1. And the important thing here is you don't need to worry about the trail. If you're doing this, the trail, because of reverse unit propagation, just magically works out. And in VeriPB, this is an expression in reverse Polish notation. Again, I'll not go into details, but this is literally all you have to write out if you're writing a propagator for all diff. Taking a very brief look at this in action, we can run our favorite, for example, clique solver on our favorite problem instance, or we can run it again and tell it to produce a proof log if we like. This produces a proof log and a pseudo boolean file, the log file and the OPB file here. And we run these through the verifier and it says, yes, that's okay, you've produced a valid proof. Or alternatively, it would say, nope, that's no good. And you can run the verify with a trace mode, so it will tell you where it gets upset. What else does VeriPB have? We've worked very hard to make this useful for solver authors. This is certainly an incremental process. The first few times I did this, I had many discussions with my collaborators that, no, the system you're trying to make me use is way too hard. I can't do this. We think now we've reached a system that, for example, you could give as a master's student project, or that you could easily have your PhD student use. We have, for example, convenient variable naming, so your proof logs could be easy to read. We support comments in the proof log, which you might think is not a big deal, but it really is. VeriPB can output traces as it goes along. And one interesting feature is we have something called a trust me assertion. So if you haven't yet worked out how to justify that one of your propagators is correct, you can just say, okay, trust me that variable x does not take the value 5. And okay, what you've produced is no longer a complete proof, but you can still verify the remainder of the proof subject to these additional trust me assertions. If you want to know how to do this in practice, so 3 papers here. At CPTAI, we explained how to do this for the all different constraint. At Int'l, we showed how to do it for subgraph isomorphism algorithms. This is interesting because these graph algorithms do all sorts of clever reasoning about degrees and paths and so on. And you might think, okay, we really need a proof language that understands graph theory. Turns out no, cutting planes is just really good at combinatorial arguments in general. You don't need anything richer than that. And then on, I believe, Thursday, we show how to do this for every clique algorithm that's ever been written and every maximum common subgraph algorithm that's ever been written. And a key point, I think, of this paper is once you've worked out how to do one clique algorithm, you can do all of the clique algorithms. So there really is no excuse for the next person who claims to have the best maximum clique algorithm in the world not to just steal our work and end up with verification basically for free. And I also give a detailed working example in this paper of I've just glossed over the details here, but if you want to see how all this works, I would suggest you take a look at the CP paper or just talk to me. So the controversial conclusion here is you need to start doing proof logging, particularly if you like doing programming by PhD students. If you tell your students to go off and produce a better solver for a problem and have a paper, even if your PhD student is not being dishonest, they will test their solver on a whole lot of benchmark instances. They'll see it seems to produce the right answer, and it's faster, they're happy, they'll produce a paper. For the greater good, I would strongly encourage you to motivate everybody you can to really try very, very carefully to make sure that you're producing a correct solver. It's very easy to get it wrong. My experience is that nearly all dedicated solvers are buggy. And I think reviewers and competition organizers should really start thinking carefully about requiring optional proof logging support as well. In the long run, we found this will actually reduce solver implementation efforts. So we think we're just about at the point where it takes less effort to develop a new solver with proof logging from the ground up than it does to develop in a conventional way and doing testing as you go along. Proof logging lets you find the bugs very quickly, very easily. And I will stop there. Thank you.